This episode of Docky's Talkies is brought to you by the letter Rho. More on that in a bit. Today we're talking about the buoyant force and how matter interacts with a fluid. So imagine you have a puddle of water or the top of a pool or something like that, and you put an object down into that fluid. Well, how does the object actually get in there? Well, it has to push the fluid out of the way. So object displaces fluid, and that makes it so the uh, the fluid essentially wants to push back. So we're going to displace fluid. We're going to push it out of the way. That means the object has to exert a force on the fluid. Newton's third law says, well, the fluid has to push back. The fluid exerts a force back on the object. And that force is what we call, ta-da, the buoyant force. It is what ultimately causes an object to feel an upward force as the fluid essentially wants to get back to its original position. The object pushes the fluid out of the way. If the object were removed there, the pressure from the surrounding fluid would push the displaced fluid back to where it came. And it's that sort of push and shove of the fluid trying to go back to its original comfortable position before that object got there that exerts a force back up on the object. So our buoyant force, hereafter we'll call it F sub capital B, for buoyant, is going to be a new force that we can add to our catalog of, normal and tension and all those other exciting forces. We're going to add that to our list, and it'll just be a new kind of force that has a couple special rules we're going to talk about now. So one, we want to think about what direction should the buoyant force exert. The way to think about this is if we take an object that's completely submerged, the fluid is going to exert forces over the entire surface of the object due to the pressure there. So you could represent little force vectors acting on the top, pushing down onto the surface there. Fluid's going to be acting along the sides of the box. And as we go deeper and deeper down, because the pressure increases with depth, we could draw those arrows as larger. So remember that fluid in the pressure in a fluid increases linearly with depth as you go down, according to the formula. Pressure equals some baseline, usually atmospheric, plus the density of the fluid, plus the acceleration due to gravity, times the depth below the surface. So as we go along the sides here, those force vectors pointing in are going to grow in size until finally, upon the bottom, which are going to go upward, those force vectors are going to be the longest. If we were to add the contributions from all of these vectors together, the ones on the side would cancel out indefinitely, and then we have an imbalance on the top and the bottom. We have the weaker forces on the bottom being canceled out and then overcome by the forces from the bottom. I think I said bottom here. The little forces on the top are being overcome by the forces on the bottom, which means if you put these all together, you get a single upward arrow, and that's what we call the buoyant force. So the direction rule for the buoyant force is always upward. The fluid will always push upward against the object because the pressure is going to be greater on the bottom edge of it at that greater depth. As long as the object has some finite depth, and most real objects do, there will always be a little bit stronger of a push on the bottom than the top, and hence the fluid will always tend to push the object upwards. This is interesting because if there were a second object, it's the same fluid, but it's a little bit deeper down. This object is going to experience the same buoyant force as this object, despite being deeper down. The force vectors here are indeed longer due to that greater pressure there. But because the top of the object is further down, these vectors are longer as well. Since the pressure increases with depth and linearly It's really just the difference between the top and the bottom. The pressure up here might be, 5 pascals. The pressure on the bottom might be 10 pascals based off, if this is a 5 meter tall object. That's huge, but, just work with me here. The same object, we push it down deeper. So maybe the top here is 15 pascals, but since pressure is increasing linearly, the bottom's only 20 pascals of pressure. So when we're comparing these vectors, which are bigger than these vectors on top are bigger as well, and they're bigger by the same proportion. So we're still going to get a pressure difference of 5 and a pressure difference of 5, so the buoyant force is constant with that depth. As long as the object is completely submerged, has its buoyant force independent of depth. It's a common misconception to think, because the pressure is getting larger, there's going to be a greater push at deeper depths, but there's also a greater push on the other side that has increased as well. So the pressure on both the top and the bottom is increasing by a constant amount, and so there's always going to be the same differential and thus the same buoyant force. How do we calculate the buoyant force? The buoyant force can be thought literally of the weight of the fluid displaced. You'll have to forgive my dog barking there if you can hear that. So we can write this literally as mass of the fluid times g. However, when we're working with fluids, particularly fluids we might not know the exact mass of, we want to instead express them in terms of their densities. So recall that density, rho, there it is, told you, is equal to mass divided by volume. This gives us the freedom to always replace kind of masses that are kind of weirdly defined or not easy to calculate with, instead, a representation in terms of the density times the volume. So instead, we will write, instead of F, or the weight F equals mg, we're going to write that instead as density of the fluid times the volume of fluid displaced times g. So this rho F here is specifically the density of the fluid. V is going to be the volume displaced. And then g is the usual acceleration due to gravity. So once our object's completely submerged, going back to this idea, it's got its full volume. It's displacing a certain amount of volume of fluid. As it goes deeper down, it's deeper down, but it's still displacing the same volume of fluid, which has the same density. So nothing changes about this formula as we go down. So this agrees with what we've already said, and that's a good thing. We want that to be true. So, summary here. We can always calculate the buoyant force by looking at the density of the fluid that the object is in. We can look at the volume of fluid displaced, and we can look at the acceleration due to gravity. A planet with a sea with a larger gravitational pull is going to result in a larger buoyant force as well. So, buoyant force. Now that we know how its direction behaves, and we know it's a way to calculate its magnitude, we can use it just like any other forces to calculate accelerations or other properties according to, say, Newton's second law. So an interesting thing we can do with this is we can take our object inside of a fluid and we draw a force diagram for it. Really simply, we have in general, there's some weight of the object, Fg going down, and then the fluid exerts its buoyant force on it, Fb. Without knowing any more about the situation, just that these forces exist, we can set up Newton's second law with F equals ma, and the net force in this case, according to our picture here, is the buoyant force going up minus the gravitational force going down. We can substitute in each of the formulas for buoyant and gravitational force, the weight, and that's going to be rho F Vg minus mg. Here the little m's go with the mass of the actual object. So again, we're working in fluid land. It's useful to compare densities. So instead of leaving the mass, which may be well known, the mass of a solid object should be well defined, but it will be useful to replace that with the mass.
So this is going to be rho O for object, VA equals rho O, F VG minus this M gets the same treatment as the first term here and becomes rho O VG as well. So your algebra senses should be going off. The volume is completely independent. So this, I drew a square here. I've been drawing bricks the whole way down. This would work with a sphere or any other shape you could imagine. The volume is irrelevant here. So we get rho OA equals rho FG minus rho OG. Now we can divide through. We want to solve for the resulting acceleration. Essentially, what we're looking for is, based off the formula we're about to derive, can we deduce the direction of the acceleration, up, down, or nothing? And that will tell us ultimately whether the object floats or sinks. So let's divide through by rho O. And we get that our acceleration can be calculated as, I'll factor out this g here, it's on both terms, and then the rho O is going to divide into each of these densities here. So it's going to cancel out this one over here, but we're going to build a ratio of the fluid density to the object density there. So fluid density over object density minus 1, that's rho O over O times g. So now this formula here not only tells us the magnitude of the acceleration, but it lets us build a criteria to let us know if an object will float or sink. So let's take a look at that, how that works. I'll write it again. The acceleration we just found was equal to the ratio of fluid density to object density minus 1 times g. So now we ask ourselves, how do the densities relate to each other? That's really all that controls what the acceleration is going to be. So if the fluid density is greater than the object density, physically that's the fluid is denser. Mathematically, that means that this ratio here, big number divided by little number, is going to be greater than 1, which when we subtract 1 from will obviously be a positive number. So acceleration is going to be positive, which if we use a normal coordinate system, it's going to be upward acceleration, aka the object floats. If the object density is greater than the fluid density, now the denominator of this ratio is going to be greater, which means that we're going to get a number less than 1. So some fractional number minus 1 is going to give us something negative. So the object is denser. A is negative. We get a downward acceleration, which means our object is going to sink. You can get really cool things to happen where if rho object is equal to the fluid density, then the acceleration becomes 0. We get a ratio of 1 minus 1 means we don't accelerate at all. And we get what we call, we are neutrally buoyant. And this is a real thing that happens. Certain kinds of fish have an organ called a swim bladder, which they can inflate the right amount to allow them to maintain neutral buoyancy at the depth that they're at, which allows them to swim a lot more efficiently. So there are ways to take advantage of getting a 0 acceleration so that you can move about the fluid without having to fight the buoyant force and all that comes with it. So this is cool. To figure out if something sinks or floats, all you really need is to compare the densities. This little factoid has been kind of twisted in recent times due to the nefarious flat Earth movement. They'll say that all you need is density. There's no gravity required. But this whole idea, this proof about the density relationship required us to have a downward force of gravity to compare the buoyant force with. So yes, all you really need is density to figure out if something will sink or float, but it's because you're looking at how something's weight compares to the buoyant force.
If the buoyant force is greater, you'll float, and that happens when the fluid is denser than the actual object per its volume. If the object is much denser, then for the same, again, here's a block of lead, here's a block of styrofoam. These are the same volume. So by our formula, rho Vg, these are going to have the same buoyant force. However, packed within that same amount of volume, there's much more mass in the lead. So that means that the gravitational force, so these are going to be the same buoyant forces, but the foam's weight is going to be much, much smaller. So that means that the foam's obviously going to rise due to that weaker weight, where the lead is going to sink as its weight allows it to overcome the upward buoyant force per its volume. Now, we can do some interesting things with this. Here's a thought experiment. I'll pose the question. You can pause the video after that and think about it for a little bit, and then we'll confirm. So here's the question. You are standing on a raft in your pool. There's walls of the pool. You've decided to bring with you your favorite giant cinder block, just cuz. And then you get bored with it, so you throw it into the pool. Plunk. And the question is, you throw heavy block into the water. Will the water level rise, fall, or stay the same? Think about it for a second. I'll be here when you get back. All right, you got your hypothesis. Let's test that. Let's see what's really going on here. When the block is outside of the water, on the force acting on the actual fluid is going to be, we'll assume the raft, it doesn't really have a mass, but you have a mass. So the force acting on the fluid due to the weight of the block and the raft is this. Force on fluid. It's going to be equal to your mass, m person g, plus the weight of the block times g. This is before we've thrown it in. Afterwards, the force on the fluid is going to be mass of the person. That doesn't change. They're still standing on the raft, plus the buoyant force. Once the concrete block enters the fluid, it's going to actively be pushing the fluid out of the way with its volume, and thus it will exert the buoyant force. Rho of the fluid Vg. Now, if we do the mass substitution, in the before situation, we can replace this with mass of the object, Vg, which, if we're assuming that we have something like concrete or marble or lead, something really, really dense, while the block is out of the water, it's actually exerting a force fluid based on its mass, on its greater density. Once it gets in the water, it's displacing it based on its volume. And so it's using the fluid density, which should be less than its mass. So out of fluid, a heavy object on a raft displaces based on its mass. So this term here was greater than this term. There's the alligator, greater. It's based on mass. In the fluid, the heavy object is displacing based on its volume. It's based off the fluid's mass for that same volume. So this is interesting. This means that once the block is actually thrown in off the raft into the pool, the water level is going to go down. It's actually able to make the water level rise more when it's pushing down on the raft with its weight and making the water level go up. Once it's off the raft and in the fluid, it's going to displace fluid based off its volume, which compared which then would use the density of the fluid, which should be less than the heavy dense material that we're hypothesizing here. So hopefully you all said the water level will go down. Usually we think an object in a fluid is going to make it displace more fluid, but it's already displacing as much as it can outside the water. It will end up displacing less, and thus for making the water level um, go down due to that lesser displacement. So hopefully you predicted the right answer. Maybe you meta predicted it based off why would we be asking a question this way if it didn't have the trick question answer? But that this is the way to kind of break that intuition. We think it's going to go up because we're putting something deeper in the water, but paradoxically almost, it is able to displace more fluid out because of its greater density. All right, that is your crash course on the buoyant force. Hopefully, this newfound knowledge will let you float through your own AP exam. Good luck and goodbye.